So in this lecture, we're going to look at some examples of integrals that we can evaluate using some various trigonometric substitutions. So starting with this one here, what I'm going to do is I'm going to start off by saying that x equal the sine of theta. Excuse me, I always forget the number. Let's let x equal 2 sine theta. And what I want you to notice here is I'm going to put a restriction on theta. I'm going to keep theta between negative pi over 2 and pi over 2. And that's okay, right? I can do that because between negative pi over 2 and positive pi over 2, the sine of theta takes on all of the values that it can take on, right? It goes from negative 1 up to positive 1. So that's going to generate all of the possible values that this function can generate for x. And you notice that's only going to generate values between negative 2 and positive 2. And that's okay, because if you look at that function that we're integrating, the square root of 4 minus x squared, the domain of this function is everything between negative 2 and positive. So that's a perfectly fine restriction to put on there, right? We're still getting every value of x that we could substitute into that expression, right? So if we do that, let's see what happens. This is the integral of the square root of 4 minus, it's 2 sine theta squared, so that's 4 sine squared theta. I'm going to leave the dx. We'll need to put d theta there. I'm just going to leave the dx for now. So I'm going to pull out that square root of 4 and then make it 2. So this is 2 times the integral square root of 1 minus sine squared theta dx. Now 1 minus sine squared theta, that's cosine squared theta. So this is 2 integral square root of cosine squared, which is the absolute value of the cosine, right? But here's where knowing what that restriction on theta was is going to come in handy. Between negative pi over 2 and pi over 2, the cosine is always positive. So the absolute value of the cosine will just be the cosine because of that restriction. So this is 2 integral cosine theta. Now let's worry about the dx part. If we differentiate up here, dx is equal to 2 cosine theta d theta. So I'm going to replace the dx with that, and this will be 2 cosine theta d theta. So this is 4 integral cosine squared theta d theta. And we've done this one before, right? We're going to use the double angle formula here. This is 4 integral 1 minus cosine 2 theta over 2 d theta. Well, that should be a plus there. I always mix the sine and cosine ones up. So that should be plus cosine 2 theta. And I can, first let's bring that 1/2 out. So this is 2 integral 1 plus cosine 2 theta d theta. So now I can do the integral. This is 2 times theta plus 1/2 sine 2 theta plus a constant. And that's nice, but I don't want theta, right? I want this to be in terms of x. Okay, so here's what I'm going to do, right? First I'm going to distribute that 2 in there. So let me come over here. Sorry, I'm out of room down there. So this is going to be 2 theta plus sine 2 theta plus a constant. Sine 2 theta is 2 sine theta cosine theta. Right, so this is 2 theta plus 2 sine theta cosine theta plus a constant. Now, I'm at the end of my rope. I need to go back to this being about x's. right? Well, first, look up here. Remember what our substitution was, right? So if I solve that for theta, right, I'm going to jump up here. X over 2 equals sine theta, which means theta is the inverse sine of x over 2. All right, so let's put that in here. This is 2 inverse sine of x over 2 plus, okay, 2 sine theta, again, come back over here. 2 sine theta is just x. What's the cosine of theta? Well, remember here, the sine of theta is x over 2. So if I draw a right triangle, put theta down here, and the sine is x over 2, then this side here is the square root of 4 minus x squared, which means the cosine of theta is the square root of 4 minus x squared over 2 plus a constant, right? And that's my not very pretty antiderivative integral, right? That's my final result for what that integral is going to equal. So let's take a look at this one. I'm seeing that 1 plus x squared down there. So the substitution I'm going to use is going to be to let x equal tangent of x. I'm thinking 1 plus tangent squared is secant squared. Right, so let's see what that substitution gives me. This becomes the integral of 1 over 1 plus tangent squared, excuse me, not x, tangent theta. 1 plus tangent squared theta squared. And what's dx going to be? Dx is secant squared theta d theta. So we'll do secant squared theta d theta. Okay, so 1 plus tangent squared is secant squared. And secant squared squared, that's going to be secant to the 4th. So this is the integral secant squared theta over secant to the 4th theta d theta. And we get some cancellation there, right? That's 1 over secant squared. But 1 over secant squared is just cosine. So this is the integral of cosine squared theta d theta. And we know how to do this, right? This is the integral of 1 plus cosine 2 theta over 2 d theta. And let's pull that 1/2 out in front, and then we'll do the integral. So this is 1/2 times theta plus sine 2 theta over 2 plus a constant. Okay, so let's take this one step further before we start trying to get back to x. This is 1/2 theta plus sine 2 theta. That's 2 sine theta cosine theta. So the 2 on the top and this 2 down here in the denominator are going to cancel. And all we have here is sine theta cosine theta plus that constant. Or what is theta? Well, if you jump back up here to our substitution, theta is the inverse tangent of x. Okay, so this is 1/2 inverse tangent of x. And what about the sines and cosines? Well, remember, again, back to that substitution. If I draw a triangle here, and give it a right angle, and an angle theta, the tangent of this angle is x. So this will be x, this will be 1. This is the square root of x squared plus 1, Pythagorean theorem. Okay, so that means the sine of theta is, it's going to be what, x over square root of x squared plus 1. And the cosine is 1 over the square root of x squared plus 1, still plus that constant. And that's it, right? This is 1/2 inverse tangent of x plus x over, you multiply those square roots together and it's just x squared plus 1, but I'm going to bring that 2 in here, so 2 times x squared plus 1 plus a constant. And that's it. Right, there's our answer. There's our integral. So I've got one more for us to look at here. And with that 9 minus x squared in the bottom, I'm going to let x equal 3 sine theta. Right? And if I do that, what happens? Then this becomes the integral of 9 sine squared theta over square root of 9 minus 9 sine squared theta. And what's dx? Well, dx is 3 cosine theta. So this will be times 3 cosine theta d theta. Now, what happens in the bottom? This becomes the integral of 9 sine squared theta over the absolute value of 3 cosine theta times 3 cosine theta d theta. All right, so here we have this same situation again. I'm going to restrict sine theta, or I'm going to restrict theta to being between negative pi over 2 and pi over 2, and that's fine. If I do that, x goes from negative 3 up to positive 3, and that's the domain of this thing. Those are all the possible x values that I could put into this integrand anyway. So I'm perfectly good with that. And if I do that, then just like we saw on the first slide, then the cosine is always positive. Right? So this is the integral of 9 sine squared theta over 3 cosine theta times 3 cosine theta d theta. We get some really nice cancellation going here. This is 9 integral of sine squared. So I'm going to do what we always do when we see the sine and cosine squared. I'm going to substitute 1 minus cosine 2 theta over 2, still d theta. And I can integrate this. I'm going to bring that 9 out. So this is 9 halves. It's going to be the integral of 1, that's theta, minus the integral of cosine 2 theta. So that's 1/2 sine 2 theta plus a constant. Now, sine 2 theta is 2 sine theta cosine theta. This one comes up a lot with these, right? So this is just 9/2 theta minus sine theta cosine theta. Okay, now I have to go back. Right, I have to go back to x's. Well, based on our initial substitution up here, theta is the inverse sine of x over 3. So I'll put that in here for theta. This is 9/2 inverse sine x over 3. Sine theta. Sine theta is x over 3, right? So this will be minus x over 3. And yeah, for the cosine, I'm going to have to go to a triangle, right? I'm going to do my triangle here, and here's theta. And the sine of this angle is x over 3. So I'm going to put an x here and a 3 here, and the square root of 9 minus x squared here. It's Pythagorean theorem. So the cosine is square root of 9 minus x squared over 3. Put that constant back in here. And we've got our answer. This is 9/2 inverse sine x over 3 minus, now look, 3 times 3 is 9. That's going to cancel that 9 up at the top. So this is x square root of 9 minus x squared over 2 plus a constant. Right? And that's it. That's our antiderivative for this function. That's our integral for this function. Okay, so what's next? You may have noticed I was Something that was conspicuously absent here. We didn't talk about doing a secant substitution, because if you watch the last lecture, the secant substitution is the one where it gets complicated. Whether or not you can you replace the absolute value of the tangent of theta with tangent of theta or negative tangent of theta is going to depend on what your values of x are, which is going to make the situation a little more complicated. Right, so that's we're going to specifically take up that case in the next lecture.